This is a video on the fundamental theorem of line integrals. The question states, evaluate the line integral over c of z squared minus 3y dx plus 1 minus 3x dy plus 2xz dz, where c is any curve connecting the points 1, negative 1, 2 and 2, 1, 0. So we see this is of the form the integral over c of f dot dr. So to make sure that this is defined, that is, any curve produces the same value for the line integral, we need to check that our vector field f is conservative. So we take the curl of f, which is the determinant of the matrix I, j, k, del over del x, del over del y, del over del z, z squared minus 3y, 1 minus 3x, and 2xz. So I take the determinant. For the I component, I get the partial derivative with respect to y of 2xz, and that's 0, minus the partial derivative with respect to z of 1 minus 3x, and that's also 0. So I get 0 minus 0i, and then minus, and for the j component, I get del over del x of 2xz, and that's 2z, and then minus del over del z of z squared minus 3y, and that's also 2z, so I get 2z minus 2z times j. And for the k component, I get del over del x of 1 minus 3x, that's negative 3, and then minus del over del y of z squared minus 3y, and that's also negative 3, so I get negative 3 minus negative 3k. So this simplifies, these all zero out, and I can say that the curl of f is equal to the 0 vector. So that means that f is a conservative vector field, which means it has a potential function. So let's find the potential function. The potential function has the property that the gradient of that potential function f is equal to the vector field. So I can say that del f over del x is equal to z squared minus 3y, so that f is the integral of z squared minus 3y dx. So I integrate. The integral of z squared dx is z squared x, or xz squared. The integral of 3y dx is 3xy. So I get xz squared minus 3xy plus some constant that may have y's and z's in them. Next, I integrate 1 minus 3x dy, and that's equal to y minus 3xy plus some constant that may have x's and z's in them. Next, I integrate 2xz dz, and that is equal to xz squared plus some constant that may have y's and z's in them. So I can put this together and see what terms I have and realize that the potential function is equal to xz squared minus 3xy, and then we see we still need a y, and the other terms are taken into account, so plus y. The constant I can let equal 0 because I just want a potential function. So now I can use a fundamental theorem of line integrals, which says that when I have a line integral over a curve of f dot dr, where f is a conservative vector field, and I know the potential function f, little f, then that line integral is equal to f of the final point 2, 1, 0 minus f of the initial point 1, negative 1, 2. So I just have to evaluate. So I plug in 2 for x, 1 for y, and 0 for z. And I got 2 times 0 squared is 0, minus 3 times 2 times 1 is negative 6, and then plus 1 is negative 5. And then I plug in 1 for x, negative 1 for y, and 2 for z. So I get 1 times 2 squared is 4, minus 3 times 1 times negative 1 gives me 4 minus negative 3, or 4 plus 3 is 7. And then minus 1, 7 minus 1 is 6. So I get negative 5 minus 6. And I can conclude that the line integral is equal to negative 11. And I'm done with the problem.